Hello everyone, welcome back to your research buddy, and in this video we will start with a new topic, that is quantum mechanics. Alright, so before starting with core quantum mechanics, let's talk about the failures of classical mechanics. Alright, so classical mechanics, that is classical mechanics represented by CM. Classical mechanics fails to explain some important concepts or phenomena like photoelectric effect, Compton effect, black body radiations, also energy exchange between radiation and matter. Okay, so such kind of phenomena cannot be explained by using classical results or classical approach. So it means we need another kind of approach. Okay, so on the failures of classical mechanics, there is origin of quantum mechanics. All right, so there is origin of quantum mechanics, and also quantum mechanics is of two types. One is old quantum mechanics and new quantum mechanics. Okay, so according to old quantum mechanics, particle represented by a wave. Okay, so particle having two characters, particle is represented by a wave in case of old quantum mechanics, and in case of new quantum mechanics, energy and momentum both are quantized. Okay, and it means we have E is equals to nh cut omega, or also this momentum is nh cut, where n is equals to 0 plus minus 1 plus minus 2 plus minus 3 plus minus up to so on. Alright, so this is the basic idea for the quantum mechanical approach. Why we need quantum mechanical approach or quantum mechanics? Because there are certain failures of classical mechanics. Out of these we have photoelectric effect, Compton effect, black body radiations, and energy exchange between radiation and matters. Right, now let's start with the black body radiation. This is the one of the first phenomena which is not able to explain on the basis of classical mechanics. So we will talk about black body radiations. Okay, so what is a black body? So a perfectly black body is one which absorbs all the heat radiations of whatever wavelength incident on it. Alright, and if a black body placed in a thermal enclosure, it will emit a radiation after it is in equilibrium with the enclosure. It means first of all a body will let's say this is black body, so first of all it will absorb all kind of heat radiations whatsoever wavelength fall over it. And if we put this black body in a thermal enclosure, right, then it will emit a radiation. After it will reach equilibrium with the enclosure. Okay, so these radiations are independent on the nature of substance. Okay, now what will be the spectral distribution of black body radiation? As we are talking about or these black bodies will emit radiation when we place these black bodies in thermal enclosure. So there will be a spectral distribution of black body radiation. Let's talk about this one. So we are getting a spectral distribution something like this one, and there are two scientists who investigated this distribution. This is just experimental findings given by Lumer and Trinksium, and they investigated the distribution of energy among the radiations by a black body at different temperatures. All right, and there is a curve drawn between intensity and wavelength at a different temperature. So we have a intensity. We can also represent this in terms of energy and wavelength, and we are getting a graph like this one. So this is first curve at temperature T1, second curve we are getting at temperature T2, and there is third curve we are getting at temperature T3. Condition is that temperature T3 is greater than temperature T2 greater than temperature T1. All right. Now if we are going to study this graph, we got some findings, so we are writing these findings in terms of results, right? So the energy is not uniformly distributed radiation spectrum of a black body. Okay, so first finding is that, as we are able to see here, we can observe from here as well that energy is not uniformly distributed. First of all, energy is increasing till this particular point, and then it is decreasing. Similar pattern for temperature T2, energy is first one increasing, then decreasing, and similar pattern for temperature T3. Okay, so first finding of this experiment is that energy is not uniformly distributed. Okay, now second finding is that at a given temperature, let's say at temperature T1, the intensity of heat radiation increases with the increase in wavelength and become maximum, right? And at a particular point or a particular wavelength, by further increasing the wavelength, intensity of heat radiation decreases. It means intensity of heat radiations increasing till this point remain constant for a certain wavelength, and then going to decrease again with the further increasing in wavelength, right? And next finding is that an increase in temperature cause and decrease in lambda maximum, right? So we can find out lambda maximum. Let's say this is the maximum of this particular curve at T1, then the lambda max is just this one. So we can write this lambda max for temperature T1, this is lambda max for temperature T2, and this will be the lambda max for temperature T3, right? And their corresponding energies are, let's say this is energy E1 for temperature T2, this is energy E2, and there is energy E3. Okay, so an increase in temperature cause and decrease in lambda maximum, as we are able to observe from this graph as well. The temperature, we are having a condition, temperature T2 is greater than T1 and temperature T3 is greater than T2 and T1. So from here itself we can observe that the maximum of these curves are shifting towards the lower wavelength. Okay, so it means the lambda max is shifting towards the lower wavelength, and at a particular time or particular point, this lambda will be constant. It means there is no change in the energy by changing in wavelength for a short duration. For this particular instant of time, we can say that lambda max at that particular instant of temperature is equals to constant, where lambda m is the wavelength or maximum wavelength for which energy emitted is maximum, and the relation is called Wien's displacement law. So lambda mt is equals to constant is also named as Wien's displacement law. And the last finding of this experiment is, with the increase in temperature causes an increase in energy emission for all the wavelengths, as we are able to observe here. For temperature T1 we have energy E1, for temperature T2 energy is increased to E2, and then for temperature T3 energy is increasing to E3. Okay, so this is the finding given by Lumer and Pringsheim on the black body radiations. All right, now what is the question? Whole scientific community is that we need to solve these results. Okay, we need explanation towards these findings. So there are number of scientists or who gave their theories to explain this spectral distribution, but one of the best explanation is given by Planck's. Okay, so we can write the next topic will be the Planck's radiation law. Okay, Planck's radiation law. So Planck gave the best possible explanation towards this distribution of black body radiation. Okay, and let's talk about it here. For the explanation of black body radiation, Planck's give an empirical formula which we call Planck's radiation law. So Planck found an empirical formula to explain the experimentally observed distribution of energy in the spectrum of black body. So the formula may be defined by using following assumptions. First assumption that was made by Planck is the black body radiation chamber is not only filled with the radiation but also with the simple harmonic oscillators or resonators of molecular dimensions which vibrate with all possible frequencies. Alright, so first assumption made by Planck is that if this is a black body radiation, so this black body is not only filled with the radiation but also with the simple harmonic oscillators of molecular dimensions. It means each and every atom or molecule of this black body will work as a simple harmonic oscillator, right? And second assumption that was made by Planck is that the oscillators or resonators cannot radiate or absorb energy continuously. Okay, but an oscillator or resonator of frequency nu can only radiate or absorb energy in units or quanta. Okay, and the magnitude is h nu. Okay, so there is no continuity in the radiation or absorbance of energy for black body radiations, but these oscillators will radiate or absorb energy in terms of quanta, right? And having magnitude is equals to h nu, where h is Planck's constant. So from here we got a concept of Planck's constant, and in other words this states that the exchange of energy between radiation and matter cannot take place continuously but are limited to discrete set of values having 0, h nu, 2 h nu, 3 h nu up to n h nu, and that is called multiple of small unit called quantum. From here we got a word quantum. Okay, so there is a derivation for this case as well for black body radiations explained by Planck's constant. Okay, so in case of derivation we are just going to write down the final derived formula. Okay, so energy density E nu represented by E nu, or you can also use U nu, in the frequency range nu and nu plus d nu depending upon the average energy of the oscillator is given by. Okay, so we are going to write down the equation for energy density in the frequency range mu and mu plus d nu is equals to E nu d nu is equals to 8 pi h nu cube over c cube 1 over exponential h nu over kt minus 1 d nu. This is my equation number 1, and this energy density is in terms of frequency. So and this relation is known as Planck's radiation law in terms of frequency. Okay, so this is Planck's radiation law in terms of frequency. And in terms of, what if we need to write this equation in terms of wavelength? So we know that nu is equals to cy lambda. So from here we can find out d nu is equals to c over lambda square d lambda, right? So use this equation 2 in equation number 1. By using equation number 2 in equation number 1, we are getting E lambda d lambda. So we are going to replace this energy density in terms of wavelength. E lambda d lambda is equals to 8 pi h c over lambda times 5 over exponential h c by lambda kt minus 1, and here we are having d lambda. So this is the equation for energy density in terms of wavelength, and there is equation for energy density in terms of frequency. All right, now from the same relation, let's say this is my equation number 3. From the same relation we can figure out Wien's law and Rayleigh-Jeans law. So we have next topic is Wien's law and Rayleigh-Jeans law. So first case is that when the wavelength lambda and temperature T, capital T, are very small. Okay, so in that case, then this exponential term, that is E h c by lambda kt, is very much greater than 1, right? Okay, so therefore one can be this one can be neglected from the denominator. So equation 3 can be written as, so we can write this equation number 3, that is E lambda d lambda is equals to 8 pi h c over lambda times 5 1 over exponential h c by lambda kt, and we have already ignored this one, so there is d lambda. This is called Wien's law, right? So this is known as Wien's law. This is known as Wien's law, which is valid for low temperature and high and small wavelength, right? So this is first case, that is called Wien's law, and in second case, when temperature T is high and wavelength lambda is also high, then what we need to do is, so that we need to expand exponential till first term. So we can write this exponential hc by lambda kt is equals to 1 plus hc by lambda kt. What we need to do is to expand this exponential till its first term. Now this we need to put in equation number 3. Okay, so by using equation number 4 in equation number 3, we got E lambda d lambda. By using equation 4 in 3, E lambda d lambda is equals to 8 pi h c by lambda times 5 1 over 1 plus h c by lambda kt minus 1, and there is d lambda. So this minus 1 and plus 1 is going to be cancelled out. We have left with A lambda d lambda is equals to 8 pi h c lambda times 5 and we got lambda kt upside and hc downside d lambda. So from here hc and hc is going to be cancelled out, and 1 lambda with lambda times 5, so we got 8 pi kt over lambda times 4 d lambda, and this is the value of E lambda d lambda. So this is the energy density in case of very high temperature and very high wavelengths. Okay, we can use this formula to find out energy density, and this is known as Rayleigh-Jeans law. This is known as Rayleigh-Jeans law. All right, so this is all about for this particular lecture, and in this lecture we have talked about Planck's radiation law, and then we have also defined Wien's law and Rayleigh-Jeans law. And before this one we have started with the postulates of Planck's radiation law, and this law we have used to figure out this particular experimental data which is conducted by Lumer and Princip on black body radiation. And that's all for this particular class. If you have any question, you can comment below. Thanks for watching this video. I'll see you in the next one. Thank you.